Linear Algebra II, Lecture 1, Vector Spaces. Let us start with a brief overview of the whole course. The major parts of this course are linear spaces, linear maps, Euclidean spaces, spectral theory for linear maps, and applications. And the structure will be that after every 2 lectures, there will be 1 tutorial. During the whole course, we will work over the field R of real numbers. Let us now start with the definition of a vector space. A vector space over real numbers is a tuple, which is usually denoted simply by V, but which consists of 4 elements: V, dot, plus, and the zero vector. So in this tuple, V is a set. The zero vector is an element in V. Dot is a binary operation where the first argument is a real number, the second argument is an element in V, and the output is an element in V. And plus is also a binary operation with 2 arguments being elements in V and the output an element in V. And these data should satisfy the following axioms. First of all, plus should be an associative operation. This means that for any elements v, w, and u in V, adding first v and w, and then adding u, should give us the same as adding to v the sum of w and u. The second axiom is that addition should be a commutative operation, which means that v plus w is equal to w plus v for any v and w in V. The third axiom says that the zero vector is neutral with respect to addition. In other words, for any element v in V, v plus the zero vector should be equal to the zero vector plus v, and this should be equal to v. The fourth axiom says that for any element v in W, there should exist an element w in W such that their sum in any order is equal to the zero vector. The next axiom says that for any element v in V and any 2 real numbers lambda and mu, if we first multiply v with mu and then with lambda, we should get the same outcome as we immediately multiply v with the product of lambda and mu. The next axiom says that 1 times v is equal to v for any element v in V. And the last 2 axioms tell us something about distributivity. So the penultimate axiom says that for any real numbers lambda and mu and any v in V, lambda plus mu multiplied with v should be equal to lambda multiplied with v plus mu multiplied with v. And the last axiom says that for any real number lambda and for any elements v in W in V, lambda multiplied with the sum of v plus w should give us lambda times v plus lambda times w. Here are some remarks. The standard terminology says that the elements of V are usually called vectors. So V is a vector space, an element in a vector space is a vector. So the zero vector is called the zero vector. Plus is the addition of vectors. So this is an operation of addition of vectors. And the dot is usually called multiplication with scalars. We can take a vector and multiply it with a scalar, with a real number. The element w in V, such that v plus w is equal to w plus v is equal to the zero vector, is called the opposite vector to V, or sometimes the additive inverse of V. So here is our first lemma. The opposite vector is unique in the sense that if we have an element v in V and 2 opposite vectors u and w, in the sense that u plus v is equal to v plus u is equal to the zero vector, but also v plus w is equal to w plus v is equal to the zero vector. Then u is equal to w. So here is a proof. Let us start with u. By the axiom of the zero vector, u is equal to u plus the 0 vector. Now, because of our assumptions, we can write our 0 vector as v plus w. So now we have u plus the sum of v and w. Using associativity, we can move the brackets to the left and say that this is equal to u plus v and then plus w. But u plus v is a 0 vector by our assumptions, so when we take the 0 vector and add to w, we get w. And so we have that u is equal to w, which is exactly what we asserted. Similarly, one can show that multiplying any vector v in v with the 0 real number, one gets the 0 vector in v. So this is an exercise. Another nice exercise is that if v and w are two vectors in v such that v plus w is equal to v, then w is equal to the 0 vector. Here is another lemma. The opposite vector to v equals -1 times v. So to prove this, since we already know that the opposite vector is unique, and we also know that addition of vectors is commutative, so we only need to check that if we add -1 times v to v, we will get the 0 vector. So let's compute v plus -1 times v. First of all, we rewrite v as 1 times v. This is one of our axioms. Now we can use distributivity to write 1 times v plus -1 times v as 1 plus -1 times v. So this gives us 0 times v, which results exactly in the 0 vector due to the one of the previous exercises. So let us now look at some examples. If we take the set v, which just consists of the 0 vector, and then define the operations in the unique way, so lambda times the 0 vector is 0 vector for any lambda, and 0 vector plus 0 vector is 0 vector for any lambda, then we get a vector space which is called the 0 vector space. All axioms are obviously satisfied because there is a unique way to define everything. Here's another example. Consider now the set V of real numbers. This set is a vector space over real numbers with respect to the usual addition and multiplication of real numbers, and by taking the 0 vector to be just the 0 real number. Again, all axioms follow directly from standard properties of arithmetic operations. We know that addition of real numbers is associative and commutative, then we have distributivity, and so on. Here's the third example. Consider the set V denoted by r to the power k, and this is a set of all column vectors of height k with real coefficients. The claim is that this set is also a vector space with respect to the component-wise operations. So if we want to multiply a vector v1, v2, and so on vk with a real number lambda, we simply multiply it component-wise. So the outcome is a vector lambda v1, lambda v2, and so on, lambda vk. If we add two vectors v1, v2, vk and w1, w2, wk, we also add them component-wise. So the sum of these two vectors is a vector where the first coordinate is v1 plus w1, the second coordinate is v2 plus w2, and so on. And we define the 0 vector as the vector where all coordinates are 0. Since all definitions are done component-wise, all axioms for the vector space follow from the standard properties of arithmetic operations applied component-wise. Here's yet another example. Consider the set of all polynomials with real coefficients. So an element of this set is a polynomial of the form a0 plus a1 times x plus a2 times x to the power 2 plus and so on, plus ak x to the power k. So k is some non-negative integer and all ai's are real numbers. So these are all polynomials with real coefficients. And this set is a vector space with respect to the usual addition of polynomials and usual multiplication of polynomials with scalars. The zero element is a zero polynomial, so the polynomial where all coefficients are zero. And again, all axioms follow directly from the standard properties of arithmetic operations applied coefficient-wise. Addition of polynomials and multiplication with scalars defined coefficient-wise. Here is a more exotic example. Consider the set of all positive real numbers. We claim that this is a vector space over real numbers with respect to the following operations. So if we take a positive real number v and we want to multiply it with a real number lambda, we define the outcome as v to the power lambda. And if we have two positive real numbers v and w, we define their exotic sum as the product. And the zero vector in this vector space will be the real number 1. And it is very easy to check that all axioms of a vector space using such definitions follow directly from standard properties of arithmetic operations. Next, let us talk about the notion of a subspace. Let V be a vector space. Definition: a subspace of V is a subset, let's say W, which has the following properties. First of all, the zero vector should belong to W. The second property, if x and y are two elements in W, their sum x plus y should belong to W. And the third property, for any element x in W and for any real number lambda, lambda.x should belong to W. If we have a subspace W of V, then this W is a vector space in its own right with respect to the operations on the original vector space V, but restricted to W. And the conditions in the definition say explicitly that a subspace W is closed with respect to these operations. So if we take two elements from W, their sum is in W, which means that W is closed with respect to addition. So the zero vector belongs to W. So W is closed with respect to taking the zero vector. And similarly, W is closed with respect to multiplication with scalars. Here are some examples. Example 1. For any vector space V, the vector space V itself is a subspace of V. So this is the obvious statement, nothing to check. Example 2. For any vector space V, the subset of V consisting just of the zero vector is a subspace of V. So let's check the conditions. First of all, by definition, zero vector belongs to this subset. Next, if we add the zero vector to the zero vector, we will get the zero vector simply by the axiom of the zero vector. And finally, it is easy to check that if you take a zero vector and multiply it with any real number lambda, the outcome will be the zero vector. These two examples of subspaces, the whole space and the zero subspace, are usually called trivial or not proper. This is especially applicable to the zero subspace of a vector space. Here are some further examples. Example 3, consider a homogeneous system of linear equations. So the first equation is a11x1 plus a12x2 plus and so on plus a1kxk is equal to 0. Then we have the second equation a21x1 plus a22x2 plus and so on is equal to 0, and so on. Then the set of all solutions to this system is a subspace of R to the power k. Indeed, let us denote by A the matrix of the coefficients of the expressions on the left-hand side in our equation. So this is a matrix A11 and A12 and so on, A1k. The second row is A21, A22 and so on and so on. And let X be the vector of the indeterminates, X1 and 2 and so on, Xk. Then we can rewrite our system as a product of the matrix A with the vector x, and the system asserts that this product should be the zero vector in Rk. So let us now check that the set of all solutions to the system forms a subspace. Of course, 0 is a solution to any homogeneous system of linear equations, so this axiom is satisfied. If you have two solutions x and y, in other words, if ax is equal to 0 and ay is equal to 0, then applying a to their sum x plus y and using the properties of matrix operations, so we have distributivity between addition of matrices and multiplication of matrices, we can write this as ax plus ay, but we know that ax is a zero vector and ay is a zero vector, so we get 0 plus 0, which is equal to the zero vector. And here we use the properties of matrix operations. Similarly, if we have any solution x to our system, so ax is equal to 0, and any real number lambda, then applying a to lambda times x, and using that for matrix operations, we can move scalars wherever we wish in the product. So we can rewrite it as lambda times ax. Ax is 0, so this is lambda times 0, which is equal to the zero vector. So this means that if you have a solution to our system and you multiply it with any scalar lambda, you will again get a solution to our system. And again, here we use properties of matrix operations. So we have checked all three axioms. This proves that the set of all solutions to a homogeneous system of linear equations is a subspace in the corresponding R to the power k, where k is the number of the indeterminates. Here is one more example. Let us fix a non-negative integer k and denote by Rx sub k the set of all polynomials with real coefficients of degree at most k. So we claim that this Rx sub k is a subspace of the linear space of all polynomials with real coefficients. So let us check the subspace axioms. First of all, the zero polynomial obviously has degree which is less than or equal to k, so it belongs to our set. Next, we know that the degree of the sum of two polynomials is at most the maximum of the degrees of the summands. Usually it is the maximum, but if we kill the leading coefficient, it might go down. But anyway, the degree of the sum is at most the maximum of the degrees of the original summands, which means that our set Rx sub k is closed with respect to addition of polynomials. Similarly, if we take a polynomial and multiply it with a real scalar, the degree of the outcome is at most the degree of the original polynomial. It is exactly the degree of the original polynomial if the scalar is non-zero, but if the scalar is 0, the degree might drop. And this implies that our set Rx sub k is closed with respect to multiplication with scalars. It is interesting to observe that Rx sub k is also a subspace of Rx sub k plus 1, or of Rx sub k plus 2, and so on. Let us now talk about linear combinations. Let V be a vector space, and V1, V2, and so on Vm be elements in V. Let us choose some scalars lambda 1, lambda 2, lambda m from R. Observe the following. The expression lambda 1 times V1 plus lambda 2 times V2 plus and so on plus lambda m Vm represents a unique element of V. This means that all possible ways to compute this expression, so we first multiply one terms and another one and then add in different order, all possible ways to compute this expression give us the same outcome, the same element of V. So this is due to our axioms of the vector space. So definition, this unique element of V, so the element represented by the expression lambda 1 times V1 plus lambda 2 times V2 plus and so on plus lambda m times Vm, so this element of V is called the linear combination of the vectors V1, V2, and so on Vm with coefficients lambda 1, lambda 2, and so on lambda m. Here are some examples. Example 1, consider the vector space R to the power 2. Let V1 be 1, 2, so the vector 1, 2, and V2 be the vector 3, minus 1. Take the coefficients lambda 1 to be 2 and lambda 2 to be minus 1. So then the corresponding linear combination lambda 1 times V1 plus lambda 2 times V2 is equal to, so we take 2, which is lambda 1, times the vector 1, 2, which is V1, and then minus, because lambda 2 is minus 1, the vector 3 minus 1. So what we get, 2 minus 3 is minus 1, and 4 plus 1 is 5. So the outcome is the vector minus 1, 5. So the vector minus 1, 5 is the linear combination of the vectors 1, 2, and 3 minus 1 with coefficients 2 and minus 1. Here is a second example, very trivial one. More or less by definition, the polynomial a0 plus a1x plus a2x squared plus and so on plus amx to the power m is a linear combination of the polynomials 1, x squared, and so on, xm. This is the linear combination for which we choose the coefficients a0, a1, a2, and so on, am. Now we can define the notion of a linear span. Let V be a vector space, and V1, V2, and so on, Vm, be elements in V. Definition: the set of all linear combinations of the elements V1, V2, and so on, Vm, with arbitrary coefficients, is called the linear span of these elements. There are many different notations which are used for the linear span of some elements. So either we have R as a coefficient set, and then the set of these elements, or these elements in triangular brackets, or just triangular brackets, or the square brackets. There are many different notations. I will use this notation mostly, V1, V2, and so on, Vm, taken into these angle brackets. And the terminology, the elements V1, V2, and so on, Vm, span the linear span, or generate the linear span. Here are some examples. So we have just seen that each polynomial of the form a0 plus a1x plus a2x squared plus and so on plus amx to the power m is a linear combination of the polynomials 1, x squared, and so on, x to the power m. This means that the subset Rx sub m is the linear span of the elements 1, x squared, and so on, x to the power m. Here's example 2. Consider the vector space R to the power k and define the following elements in this set. So let E1 be the vector which has first coordinate 1 and the rest are 0. E2 is a vector where the first coordinate is 0, the second is 1, and then the rest is 0. And so on. The last element ek has all coordinates 0 except from the last one, which has coordinate 1. So for any elements x1, x2, and so on, xk in the set of real numbers, we can write the vector x1, x2, and so on, xk as x1 times the vector 1, 0, and so on, plus x2 times 0, 1, 0, and so on, plus and so on. So in other words, we can write it as x1 times e1 plus x2 times e2 plus and so on. Consequently, the space R to the power k is the linear span of the elements e1, e2, and so on, ek. Let us now establish some basic properties of the linear span. First of all, proposition: let V be a vector space and V1, V2, Vm be elements in V. Then the linear span of these elements is a subspace of V. So to prove that it's a subspace, we need to check 3 conditions. First condition: the 0 vector should belong to our linear span. But of course, we can write the 0 vector as the following linear combinations. It's simply the linear combinations of our elements with all coefficients being 0. So if you take 0 times v1 plus 0 times v2 plus and so on, it will be sum of 0 vectors, which is 0. So, and of course, this is an element in our linear span, so the zero vector belongs to the linear span of our elements. Next, we need to check that our linear span is closed with respect to addition of vectors. So if we have two elements in the linear span, so each element is a linear combination of V1 and so on Vm. So we take one such linear combinations with coefficients lambda i's and another such linear combination with coefficients mu i's. And we try to add them. So using the axioms of the vector space, we can rearrange summands and then use distributivity to rewrite this as a sum over all I from 1 to m, vi times the coefficient lambda I plus mu I. And this is manifestly a linear combination of our elements, and so it belongs to our linear span. Finally, given an element in our linear span and a real number mu, so we can multiply mu with our element with this linear combination with coefficients lambda I. Then we can use distributivity and our axioms for multiplication to rewrite it as a sum over all I from 1 to m. The coefficient will be mu times lambda I times vi. And this is again manifestly a linear combination, so it belongs to our linear span. And everything what we did follows directly from the axioms of a vector space. And here is one more useful property, the so-called redundancy property for linear spans. Let V be a vector space and V1, V2, and so on Vm be elements in V. Let W be some linear combination of the elements V1, V2, and so on Vm with some fixed coefficients. Then the linear span of V1, V2, and so on Vm is equal to the linear span of W, V1, V2, and so on Vm. So if we add a linear combination of the original elements, it does not affect the linear span. So to prove this, let us introduce the following notation. Let us denote by m the linear span of V1, V2, and so on Vm, and by n the linear span of V1, V2, and so on Vm, and additionally W. So here is a proof. Since 0 times W is a zero vector, then the linear combination mu1 V1 plus and so on plus mu m Vm can be written as 0 times W plus mu1 V1 and so on plus mu m Vm. In other words, each element in the first linear span also belongs to the second linear span, so M is a subset of N. Next, recall that W was a linear combination of the VI's with coefficients lambda I. So we can write arbitrary linear combination of W, V1, V2, and so on Vm in the following way. So consider the linear combination mu W plus mu1 V1 plus mu2 V2 plus and so on. So we write mu times W, and now we use the expression of W as a linear combination of the VI's with coefficients lambda i's, and then plus the linear combination of VI's with coefficients mu i's. Again, we use the axioms of the vector space, distributivity, and then we rearrange summand and use distributivity again. So we can rewrite this expression as a sum over all I from 1 to m, mu times lambda I, it comes from this summand, plus mu I from here times Vi. And this is manifestly a linear combination of V1 and so on Vm. So this element belongs to N. It's a linear combination of V1, V2, and so on Vm and W, while this element belongs to M. It's only a linear combination of the VI's. In other words, N is a subset of M. And so N and M are equal, exactly as stated in the proposition. Okay, so that's all. Let's also formulate some more exercises, problems, and questions. Question 1. So prove that V plus V is equal to 2 times V for any V in V. Question 2. Prove that lambda times 0 vector is equal to the 0 vector for any lambda real number. Question 3. Does the set of all polynomials of degree exactly k form a subspace of Rx sub k? Question 4. Prove with all details that the expression lambda 1 times v1 plus lambda 2 times v2 plus and so on plus lambda m times vm represents a unique element of V. Question 1. Prove with all details, then adding two linear combinations of the VI's with coefficients lambda I and mu I, we will get a linear combination of the VI's with the coefficients lambda i's plus mu i's, directly using the axioms of the vector space. Thank you very much. See you next time.